Welcome guys sa data structure Prefinal lesson 2, and we're going to discuss about graphs. Okay, so we go now with our introduction. Okay, in previous chapters you learn various ways to represent and manipulate data. This chapter discusses how to manipulate graphs. In 1736, the following problem was posed in the town of Königsberg, now called Kaliningrad. The river Prefinal flows around the island Kniefhof and then divides into two. So this is the representation of the island. Merong island dito, may island dito. Ito mga land, ito yung bridge. Okay? So the river was four land areas A, B, C, D. Where's the A, B, C, D. So yun yung mga land. These land areas are connected using 7 bridges, and the bridges are called or labeled A, B, C, D, E, F, G. Okay, so the problem is starting at one land area, is it possible to walk across all the bridges exactly once and return to the starting land area? So nung gumawa si Euler nung 1736 ng graphs, okay, which is the first graph ever created to solve a problem, a bridge problem. And yun, after creating this, he answered the question in the negative, meaning no one can return to the same land by just crossing the bridge once. Okay, so by just looking at the graph, he was able to answer the problem. Over the past 100 years, graph theory has been applied to a variety of applications. Graphs are used to model electrical circuits, chemical compounds, highway maps, and so on. They are also used in the analysis of electrical circuits, finding the shortest route, project planning, linguistic, genetics, and social sciences. So for this chapter, you learn about graphs and their applications in computer science. Okay? Graphs definitions and notations. To facilitate, simplify our discussion, we have a few definitions terminology from set theory. So we already discussed the symbols from discrete structure 1 in your first year term. Okay, so we have the set, which means belongs to, elements, and this one is subset. Okay, subset of. Okay, those are the symbols that we're going to review in dealing with graphs. This is the intersection. The U is the union. Yun means the union. And we have the Cartesian product for the pair order or ordered pairs. Okay? So a graph G is a pair. Okay? G equals VE. Okay, where V is a finite non-empty set called the set of vertices G, which is E is subset of B, the Cartesian product of V. That is, the elements of V are pairs of the elements of B. E is called the set of edges of G. G is called trivial if it has only one vertex. Okay, so let VG denote the set of vertices and EG denote the set of edges of a graph. Okay, so yung V set of vertices, yung E set of edges. Okay, so let G be a graph. A graph H is called the subgraph of G if VH is part or a subset of V, and E is a subset of EG. That is, every vertex of H is a vertex of G, and every edge in H is an edge in G. A graph can be shown pictorially. The vertices are drawn as circles, and the label inside the circle represents the vertex. And in a directed graph, the edges are drawn using lines. In the directed graph, the edges are drawn using arrows. So these are undirected graphs. Okay, so we have a map here and two other graphs representing undirected graphs. They are also called the non-arrow lines or edges. Okay, so these are the directed graphs, or what we call the digraph. Okay, so when we collect the sets of the vertices, we use the notations for a set. Okay, so a set V is equal to 1, 2, 3, 4, 5, So we get the vertices, no? 1, 2, 3, 4, 5. Okay? For G2, we have 0, 1, 2, 3, 4. For G3, G3 has a longer or more vertices. For the edges, we collect the set, we make the set as a set of pairs, no, ordered pairs for the digraph or the directed graph. Okay, so meaning this edge comes from point 1 to point 2, or vertex 1 to vertex 2. Okay, and 1, there's an edge coming from 1 going to 4, there's an edge coming from 2 going to 5, so on and so forth. So this is how we make the sets for the vertices and the edges. Let G be an undirected graph. Let U and B be two vertices in G. Then U and V are called adjacent. Okay, so yung U and V daw are vertices if they have the same edges, then they are adjacent vertices. No, if there's edges from one to another, that is UV is an element of E. So an edge incident to single vertex is called a loop. So kung walang ibang vertex ang isang edge, no, bumabalik sa isang loop, sa isang vertex, then it is called a loop. If two edges U1 and 2 are shared with the same pair of vertices U and V, then U1 and 2 are parallel edges, and the graph is called the simple graph if it has no loops and no parallel edges. So let E, U, B be an edge in G. When we then say that edge G is incident on the vertices U and V. Okay, so we have the incident edge. If we say that the edge E is an edge coming from U going to B. The degree of U, written as deg U or du, is the number of edges incident with U. We make the convention that each loop on a vertex U contributes to the degree of U. U is called an even odd degree vertex if the degree of U is 7 or even or odd. There is a path from U to B if there is a sequence of vertices U1, U2, UN such that U is equal to U1, UN is equal to V. Vertices U and V are called connected if there is a path from U to B, and a simple path is a path in which all the vertices except possibly the first and last vertices are distinct. A cycle in G is a simple path in which the first and last vertices are the same, and G is called connected if there is a path from vertex to any other vertex. A maximal subset of connected vertices is called a component of G. Okay, so those are the terms defining a graph. Okay, so we have simple graph, we have a loop, we have a parallel edges, we have incident edges, simple path, we have the distinct, and we have the component, no, of a graph. Let J be a directed graph, and let U and B be two vertices in G. If there is an edge from U to V that is U to V, there is an element of V, we say that U is adjacent to U and to V, and V is adjacent from U. So the definition of the paths and cycles in G are similar to those for undirected graphs. G is called strongly connected if only two vertices in G are connected. Consider the following directed graphs in figure 7.4. In G1, 1, 4, 5 is a path from vertex 1 to vertex 5. There are no cycles in G1, and G2, 1, 2, 1 is a cycle. G3, 1, 0, 1, 2, 4, 3 is a path from vertex 0 to vertex 3. 1, 5, 6, 7, 8, 9, 10 is a path from vertex 1 to vertex 10, and there are no cycles in G3. Okay. So those are the ways we can describe or identify the loops and the directed or simple path of a directed graphs. Okay, so which is the same with the undirected graphs. We go now with the graph representation. So how we save or store a graph in a computer memory. So we have what we call adjacency matrices, no? So this is a deriving formula, okay, for finding the adjacency matrices of a graph, no? So in a directed graph, if bi and vg, or they are called the vertex, which is the element of uh, graph E, is equal to 1, it follows that the adjacency matrix of an undirected graph is symmetric. If it's symmetric, they have the same number of vertices, the same number of edges. No? Consider directed graphs of figure 7.4. The adjacency matrices of the directed graphs G1 and G2 are as follows. So kapag may 0, walang vertex yun, or walang edge connecting them. Kapag may 1, there is an edge, no, connecting the two vertices. Okay, so that's how a computer store, no, the elements of a graph. We have also what we call adjacency list. Let G be a graph with an n vertices where n is greater than 0. So let set B equals B1, B2 until Vn. In the adjacency list, representation corresponding to each vertex V, there is a link list such that each node of the linked list contains the vertex U, such that VU is an element of set E, or the graph E. Because there are n nodes, we use an array A of size n, such that the AI is a reference variable pointing to the first node of the linking list containing the vertices to which VI is adjacent. Clearly, each node has two components, a vertex and the link, because we are using a linked list for the storage of the adjacency list. No? So the component vertex contains the index of the vertex adjacent to vertex I. So to determine the vertex, we store it in a array format reference. No, for example, the I is the index number, and the A is the name of the array. Consider the directed graphs of figure 7.1.4. Figure 7.2.1 shows the adjacency list of the directed graph G2. So remember, if there is an adjacency list, then there is a linked list involved in the program. Okay, so this is the representation of adjacency list of graph 2 as shown in figure 7.4. No, so again, this is the adjacency list of the directed graph graph 3 shown in 7.4. Okay, so you can see the array uses the linked list, no, to store the graph, no, both graphs in the computer's memory. We go now with operations on graphs. No? Now that you know how to represent graphs in computer memory, the next obvious step is to learn the basic operations on a graph. The operations commonly performed a graph are as follows. Create the graph, clear the graph, determine whether the graph is empty, traverse the graph, and print the graph. So before we create the graph, we first clear the contents of the graph, and to determine whether it's empty, then we use a function, no, to determine if it's empty. And if it's empty, then we use another function to create the graph. Then after creating contents for the graph, we traverse, meaning we visit or we go inside or collect the data from the graph, and then we can also print the graph. So we will add more operations to graph when we discuss specific application or a particular graph later in this chapter. How a graph is represented in computer memory depends on the specific application. For illustration purposes, we use the adjacency list or the linked list representation of graphs. Therefore, for each vertex V, the vertices adjacent to V in a directed graph, also called the immediate successors, are stored in the linked list associated with V. To manage the data in a linked list, we use the class unordered linked list to discuss in linked list chapter. The labeling of the vertices of the graph depends on specific application. If you are dealing with a graph of cities, you could label the vertices by the names of the cities. However, to write algorithms to manipulate the graph as well as to simplify the algorithm, there must be some ordering to the vertices. That is, we must specify the first vertex, the second vertex, and so on. Therefore, for simplicity, throughout this chapter, we assume that the end vertices of the graphs are numbered from 0 to n minus 1. However, it follows that the class we will design to implement the graph algorithm will not be a template. Graphs as ADT. In this section, we describe the class to implement graphs as an abstract data type or ADT and provide the definitions of the functions to implement the operations on a graph. So we have a sample code here. The following class defines a graph as an ADT. So we first create the class or the object called graph type. Then we declare it a public, and under the public we declare a function, no, to know if the graph is empty, and it will return a true or a boolean type data or information. So what is the purpose of the isEmpty function? Function to determine whether the graph is empty. Then next we create or execute the create graph function to create a graph, and then after creating the graph, we clear the graph by the clear graph function, and then after clearing the graph, we print the graph, and then after that we do the traversal or the visiting of the vertices, no? So by visiting, we use the depth first traversal and also with the DFT vertex function, and after that we will use the breadth first traversal and then the constructor and destructor to clear or to clean the to empty the created graphs. Okay, and then finally we will perform another depth first traversal. The graph at the node specified the parameter vertex. This function is used by the public member functions depth first traversal and DFT at vertex. Post conditions starting at the vertex, the vertices are printed using the depth first traversal algorithms. The graph is empty if the number of vertices is 0, that is, if g size is 0. So remember, the g size is a variable and can contain an integer or a boolean value of true or false. Therefore, the definition of function is empty is as follows. The bool means boolean, or it will return a boolean type data. Graph type is empty function. Construction, we return g size equals or is equal to 0. The definition of the function create graph definition of the data's input into the program. For illustration purpose, we assume that the data the program is input from a file. So these are the example files that will be created or inputted into the created graph. The first line of input specifies the number of vertices in the graph, and the first entry in the remaining lines specifies the vertex, and all of the remaining entries in the length of the last specify the vertices that are adjacent to the vertex. So each line ends with the number -999. Using these conventions, the definition of the function create graph is as follows. So we create the graph type, create graph function. So how do we create? We first create the variable find name. This is also a variable vertex, variable adjacent vertex, and then we use the if function, if condition, so that if the graph is not empty, then make it clear graph function. Okay. Then we, after clearing the graph, we put the file or the data inside the graph. So if there's an error, then it will return this cannot open file message. We use again the for loop to cycle through the graph in checking and saving or storing the information in the graph. Okay. The function clear graph empties the graph by deallocating the storage occupied by its linked list and then setting the number of vertices to 0. Okay. So we are using the for loop to set the g size to 0 for all the vertex to clear the graph. The definition of function of bring graph is given. Bring graph function, we use also the for loop to cycle through the graphs or to cycle to the vertices of the graph and determine if it has a g size equivalent to 0. The definitions of constructor and destructor are also are as follows. Okay, so by constructor we mean we construct another object of the graph. Okay? If it's fine, the G size is equal to 0, then construct a new object called under unordered linked list. No? And then the destructor will clear all the contents or the vertices and edges of the graph. So that's all for the operations of graphs. No? We go now with graph traversal. When we say graph traversal, we are visiting all the vertices inside the graph. So parsing a graph requires the ability to traverse the graph. This section discusses the graph traversal algorithms. Traversing a graph is similar to traversing a binary tree, except that the traversing a graph is a bit more complicated because the difference between binary tree and the graph, the binary tree has no loops while the graph has loops. Now, if graph has loops, then it will be more complicated to traverse than the graphs that that is not having any loops inside the linked list. Therefore, we must keep track of the vertices that have been visited. We must also traverse the graph from each vertex that has not been visited of the graph. This ensures that the entire graph is traversed. The two most common graph traversal algorithms are the depth first traversal and the breadth first traversal. The depth first traversal is similar to the pre-ordered traversal of binary tree, and the general algorithm is as follows. For each vertex B in the graph B is not visited, start the depth first traversal at B. So whenever a vertex is not visited, then the start of the depth first traversal will begin. So consider graph G3. So in using the depth first ordering of the vertices of graph G3, the vertices will be as follows. No? The traversal of vertices will be as follows: 0, 1, 2, 3, 4. So you will see that it is from left to the right on top. Okay? And it is not going down. No? While for the breadth first, it will start at 0 but not start at left, from left to right also, but it will not be on the top, but it will be going down on vertex 5 and vertex C instead of going to vertex 1 to vertex 2. Okay, so that's the difference between the two breadth first and depth first algorithm. Okay, so this is the example code for the algorithm for the depth first, no, the FT. So we create a parameters V representing the if it's visited or not, and the visited boolean for the name of the array. Okay, so we use the for loop to cycle or traverse inside the graph. Okay, so this is the depth first traversal implementing the functions. Okay, so for loop uses to traverse or to cycle through the graph while determining if the vertex has been visited or not. Okay, while in the first traversal, you can see that it goes from 0 to 1 and 5 and 2 and 3, no, going below, not going to the right, no. And this is the breadth first traversal functions, implementing the functions. Okay, so we have the for loop, we have the variable, and the array, no. Again, we have the for loop here using the accessing the array and then determining if it's visited or not. Then there is a condition here to determine, no, if it will be continue cycling or traversing. And that's it for the graph discussion for the Prefinal lesson 2 of data structure and algorithm.